Great news. Okay, so you encountered percent yield in your last lab, where you made the lead iodide, that yellow crud, and then you did some math to figure out how much you should have made. If everything goes proper, we very rarely make as much product as we calculate we should.
Yeah, I made more.
Yeah, probably because not all the water got out of there, or there was some mismeasurement or something. Or you didn't allow your crystals to dissolve before you filtered.
Oh, I did.
Okay, well, then you broke chemistry. But it doesn't matter. Anyway, most of the time, you get less than you calculate you should get. And the ratio of how much you actually got to how much you calculate you should got is percent yield. So if you get if you have a 90% yield, that means you made 90 grams out of a calculated 100 grams. So you do a stoichiometry, maybe it's a limiting reactant stoichiometry, and you get to your end product in grams. That is your ideal value or your calculated value. And then the actual value is what you get in lab. It's just a simple ratio. Couldn't be easier. So if 90 grams of product is collected from a process that was calculated to produce 21 grams, what is the percent yield? So it's just 19 divided by 21. So you calculated you should have made 21 grams, but you only made 19 grams. So what's the percent yield?
90.5.
90.5%? See how this works? It's just what you actually got over what you calculated you should have got if everything was perfect. The tricky part of percent yield is making sure, and a few of you messed this up, making sure that you're comparing grams of the same thing. So in your lab, it was grams of PBI2 over grams of PBI2. The grams of PBI2 you got on day 2 divided by the grams of PBI2 the limiting reactant said you should have made. That's your percent yield. Questions so far? No. Okay, this one we're going to do together, and the last one will be for you, I think. If 35 grams of zinc reacted with excess copper sulfate, like that. Now again, this is only going to be a 1T chart because we don't have to worry about the other thing. It says we have as much copper sulfate as we need. So 1T chart, one reactant, one product. And only 32.5 grams of copper are recovered. You're doing this tomorrow in lab, I think. Holiday, yes. Wednesday and Thursday. Really cool lab, one of my favorites. So you're doing this in lab. You're going to get some copper sulfate solution, and you're going to add zinc to it. And the zinc's going to go in, do a single replacement reaction, and kick out the copper. And then you're going to collect the copper. So, how do you do this? Well, it starts like this. Like everything in stoichiometry, it starts with a T-chart. All right, what goes in this box?
Whoa.
Nothing. What goes in here?
Something.
Something. What's something?
1.
No.
33.5 grams.
35.0 grams of zinc. Remember, how many things in each box? 3. 3 things. A number, a unit, and a label. Conversions have how many units and labels? 2. That's why you never start with a conversion. So I got my 35 grams of zinc, and I ultimately want to know grams of copper. That's my goal. So what's my next step? What? What is? What thing? Zinc. So we're going to convert our zinc from grams to moles. And the gram to mole conversion comes from?
Periodic table.
Periodic table. Periodic table tells me 1 mole of zinc is, apparently it's 65.4. 65, let me try that again. 65.4 grams of zinc. Good so far? All right. If you're with me so far, give me a thumbs up. Been doing this for a while, so I want to make sure we're all on the same page. Okay, so now I got zinc, moles of zinc. What do I do next?
We want to get gram. No, we want to get
Mole ratio.
Use the mole ratio.
Yeah.
I want to convert my moles of the unit I have, zinc, to the moles of the unit I want, copper. What is the ratio there in my equation?
1 to 1.
1 to 1. I love it when it's simple. 1 to 1. Okay. And then finally, we're going to take our moles of copper and convert it to our grams of copper. And where do we get the gram mole? Periodic table. Periodic table tells me that a mole of copper weighs 63.6. So 1 mole is 63.6 grams. And then we can do some math, and this will be the grams of copper calculated in this case, which is the ideal value. So how many grams of copper would I get if everything was perfect?
34.
34.0? 34.0 grams of copper. So that's my ideal value. If everything was perfect, that's how much I would make. But it says in the process that I used, I only acquired 32.5 grams. So I'm going to put that over my calculated, 32.5 grams copper actual, and the product or the quotient of these two is going to give me a percent yield. What's my percent yield?
95.6.
95.6? Can I get a confirmation on that?
Yes.
School is where kids go to watch adults work.
95 or 95.6.
95.6. Okay. So this process is 95.6% efficient. That's its yield. In real life, a lot of chemical processes have single-digit yields because we're trying to make something that something doesn't want to get made. And you could get books and movies written about you if you improve that percentage, like what Fritz Haber did. Want to know more? Google Fritz Haber. All right, next. There is another thing you can use percent yield for. If you know the percent yield of a process, you can predict how much you should get. For instance, let's say you calculate that you should get 100 grams of your product, but you know the process only has a 60% yield. How much should you expect to make? 60 grams. Okay, so it's just a matter of reflipping the percent yield calculation. So if this process, 2 sodiums and 1 chlorine makes 2 sodium chlorides, has a percent yield of 88.6, how much sodium chloride should be produced from 17.2 grams of sodium? Enough. Great. So I'll go a little faster. 17.2 grams of sodium. We're going to put grams of sodium here, convert it to moles of sodium. Good?
Yeah.
And the periodic table tells me 1 mole of sodium is, I believe, 23.0 grams.
Yeah.
And then 1 mole of 2, actually, because we're going to sodium chloride. And again, excess chlorine, we have as much chlorine as we need, so it tells us that sodium is going to be a limiting reactant. So 2 moles of sodium is required for 2 moles of sodium chloride. And for every 1 mole of sodium chloride, I think it's 58.5 grams of sodium chloride. Is that right? 58.5? A sodium and a chlorine? Let's pretend it is. So how much do we calculate we should make? What's the ideal value? 58.44.
Oh, Friday, see ya.
Oh, okay, yeah, 58.44. So it's 58.4. I'm just going to keep it 5. Okay, so if everything was perfect and it had 100% yield, how much sodium chloride would we make?
43.7.
42.7 grams of sodium chloride. Would you say so? 43.0? Better? Okay. 43.7, okay. 43.7 grams of sodium chloride. This is still the denominator of our percent yield calculation. The bottom is always the calculated value. But in this case, we want to know how much we would expect to make if the percent yield was 88.6%, 0.886.
So we multiply?
Yes.
Good thing I have a calculator.
Yeah, exactly.
Times 0.886. 38.7.
38.7 grams expected.
Yeah.
17.
You would expect to make 38.7 grams of arsenic. Questions?
No, it's
Yay, we're done with lecture for this unit. If you have no questions, you can go and work on your own.
Okay.
We have one more lab and then the
I have a
test is
question.
later on this week, I think. Yes,
Was there just an assignment and skills test from Friday?
yes.
Okay.
That sounds familiar. Any other questions?
Did
Bye, Seamus, bye.